Have you ever wondered why cars come in different shapes and what makes some more aerodynamic than others? Today we're diving into something fascinating, the hidden worlds of airflow around cars, and specifically comparing two versions of popular Peugeot 206. In this comprehensive training, we go over at Peugeot 206 Aerodynamics in great detail, comparing its famous hatchback and sedan models. Using Ansys Fluent tool, we'll reveal the invisible forces at work when which air rushes over and around the vehicles. You'll be amazed to see how a simple change in the back design from a hatchback to a sedan creates dramatically different pattern in the air. Aerodynamics is an important part of automobile engineering that affects numerous factors about vehicles' performance, including how well it handles, how much petrol it uses, and its top speed. Since it came out in 1998, the Peugeot 206 has been a popular small car on the market. It's a great example of how small changes in body shape can have a big effect on aerodynamic properties. Stay with me as we uncover the secrets behind vehicle aerodynamics and discover why these differences matter in the real world. What we're about to see might just change the way you look at cars forever. Welcome to CFD Land. Welcome to the realm of data-driven simulations. They will. Avoiding from any waste of time, I'm gonna start from Ansys Workbench. So, just for beginners, in order to open Ansys Workbench, all you have to do is to just type Workbench in your search tool, and down you can find Workbench, which is installed on their system. For example, mine is 2024 R2 version. Then you will have access to all the modules prepared by Ansys Fluent on the left side in the toolbox. But what I'm gonna actually use in this solution is each of the components. I mean the geometry, the standalone mesh, and then the solver. So this time I'm gonna scroll down to find components beneath the component system and drag and drop the geometry module to my workspace. Then this time, again, I'm gonna use Ansys Splish Name to edit and modify the geometry. So I right click on that and choose New Space Claim Geometry. Very well. So let's start by drawing the geometry of both two cases. But in this first one, I'm gonna draw just the hatchback version of 206. So this is what we're gonna do. Actually, we've got a surrounding zone in which the air is filled and the model car is subtracted from it. But upon this, I'm gonna draw another zone which is not subtracted. I mean, it's an independent part, which helps us later in Ansys Meshing to have more accurate element distribution behind the vehicle. Because this is actually going to help us in order to decrease the computational costs. And one more thing is that actually we've got the initial sample of each of these cars. And these are accessible on our website, but you can actually search on the net for websites such as GrabCAD in order to download them. So in the initial step, I'm gonna import these geometry model. So through the Assembly tab and then File, I just need to locate the geometry file. So here it is. And besides that, you have to know that this is IGS format file, so I have to change the this actual field to all files so I can see these format files. So let's start by hatchback version of 206. Alright, this is a model, but we cannot have a perfect view for now, so by just clicking on this option, a trimetric view would be shown, and now I can see my model, which is located just right on the origin. And anytime if you wanted to get back to this view, you just need to click on this. Alright, so I press escape button on my keyboard to undo everything and get back to the sketch tab. Because I'm gonna draw a sketch tab, a sketch zone here. So first thing, I'm gonna draw the cross-sectional view of this rectangular zone and the Z actual direct, which is perpendicular to XY plane. So as I click on this Z axis and then have my new sketch from Design tab, by just click on Sketch mode, I can have this view. And once again, if I click on Z axis from this origin box, you can have a normalized view on that. So what I'm gonna do is to pick up the rectangle tool and start from a point just like somewhere around here and draw a rectangle just like this. But you can, as you can see right here, you can draw the dimensions and define them right now. So for example, regarding these actually width of the car, I'm gonna have more extended zone, somewhere like let's just cheat 12 meters. So I enter 12 meter and then M, which stands for meter. And again, in order to jump to the other dimension, I mean the vertical length of these butts, I'm gonna press tab button on my keyboard. And at this time, the vertical length should be lower. So I decrease that to 6 meters. And then just press enter. Alright, so you can see right now, this actually is defined with exact dimensions, but it is not located very well. In order to draw again the dimensions from each side regarding this axis, you can have the dimensions tool up here. So from now on, as you click on each of these edges, or even select 2 different axes, you'll have the distance between them. So let's start by this vertical length. I wanna keep it fixed. So I click here, from me actually define this vertical length, which is 6 meters. For now you can see in millimeter SK. And actually the other one, but this time I'm gonna pick this edge and then click on this vertical guide and define this distance. So we already know that in order to put this car in the middle of our zone, I'm gonna define 6 meters, or in other words, 6,000 millimeters. Just like this. And the other one is the vertical distance between these 2 edges. So regarding the wheels of the car that are not depicted right now, I'm gonna actually consider a vertical length in order to let the air pass from beneath the car. So for this aim, I'm gonna use 700 millimeters. And this would be perfect. One more thing that I'm gonna mention here is that in order to zoom in or zoom out, all you have to do is to press Shift button on your keyboard, and then just by pressing the wheel mouse, you can zoom out or zoom in. All you have to do is to just move it toward the upside or downside. Alright, so our sketch is ended, and we can end sketch editing. For now, as you can see, it's just a surface, and it has to be pulled for, let's just say, extruded to have a rectangular box. So you can find pull option up here. So I activate that, and then I click on this surface. But before dragging and dropping it through this way, I'm gonna show you that if I drag and drop it right now, automatically the car inside would be subtracted from the domain. So let me escape and exit this tool in order to change the view to the transparent. And now you can see that if I hide the car, this is the zone, and actually it is not subtracted so very well. We can keep on this method. So I press Ctrl Z in order to get back to uh, initial surface and draw it again. So once again, I drag and drop, but before leaving this mouse wheel or left mouse click, I'm gonna define the pull actually dimension on this side. So for now you can see that it's about 400 and 700 millimeters, but I'm gonna increase that to 5 meters or 5,000 millimeters. Just like this. You can see it is actually parameters and it is accurate. So once again, I click on this side. I'm gonna extend this surface through the back side or rear of the vehicle for 15 meters. So once again, I type 15 or 15,000 millimeters to draw this box. And now we're done. So I press escape button and exit this tool. So for now, you can see that we've got a solid zone, which I can change the name to the, for example, air zone. And we've got the car that I'm going to change the name to the car. But as you can see in here, we have to subtract this car from our air zone because actually computational zone established from the fluid regions. So the car, which is a solid region, should be subtracted, and it is not taken into account to our solution. So in order to subtract it, you can pick up the combine option and then click on our rectangular zone, and then you can see that this software asks for the cutter object. So prior to selecting the cutter object, I'm gonna uncheck the keep cutter option here. And then you can click on the car or you can select it through the 3 outline. So it may last for a minute and now it is done. So once again, I quit this tool and let's get back to our 3 outlines. So you can see that the air zone is here, and the solid, which stands for the car, would be on the other zone. So there's no need to have and keep these 2 objects here. So simply I'd press delete on the keyboard to delete them. So what changes actually has made? Let me hide this car zone, and now you can see that it is subtracted from our domain. And there wouldn't be any car in here. So the solid zone is just removed. All right. You can just keep the solid zone or you can suppress that. So I prefer to suppress it so it wouldn't be taken into account to our solution. And now I can say that the general outline of our geometry is done. But as I said in the beginning, I'm going to draw another region in order to guide us through generating elements around the vehicle, because the domain is too extended, and if I'm going to generate elements all over it, it will result in high number of elements, and that will increase the computational costs. So once again, I'm going to draw a sketch, and again on this XY plane, and this time it would be smaller. So let me zoom in a little bit, and once again pick up the rectangle option and draw this rectangle just like this. So for this one, I'm gonna have, for example, 5,000 millimeters, and for the vertical lens, it would be maybe 3,000 would be appropriate. So in order to have the precise values, I'm gonna define both dimensions, and once again, in order to put it just in the middle, I define these 2 lenses. So this would be 2,500 millimeters, and this is just what I was looking for. So I end the sketch, and once again get back to our trimetric view, and pick up this surface in order to extend it through all sides of the domain. So as you can see, the pull option is selected, and I click on surface button. So now I'm able to drag and drop these surface through each side. But don't forget that you have to click on no merge option, so it wouldn't be merged with the other zones. Because we're going to keep this zone, and it will be actually eradicated later on in the Ansys meshing. So for now, I just drag and drop it through this side, and another time through the other side. So in order to have access to this side, I'm gonna hide this air zone, and then click on this side of this rectangular or the smaller zone and drag and drop it till the end. And now let's get back to our view and have the air zone, and you can see that this zone is actually extended, and you have to know that it wouldn't make any problem later. You'll see that. So I'm gonna rename this zone to for example, the guide zone, because it's gonna guide us through generation of the elements. Alright, so I can say we're done with the geometry step, so I create Ansys space claim. And then I have to drag and drop the mesh module. So you can find that once again down here. All you have to do is to drag and drop it, but this time I'm gonna drop it on the geometry. So the geometry will be automatically transferred to Ansys meshing. Very well. So this is Ansys meshing, and we have two major missions in Ansys meshing. First, we have to generate the proper mesh for this model, and the second one is to select names for each of the boundaries so we can use later in a solver. So let's just start from generating of the mesh grid. So you can see mesh in the tree outline. So first thing that you have to check is the physics preference. So by default it would be on mechanical, and you have to change it to CFD, because it is a CFD simulation and generation of elements is very sensitive. And by right-clicking on mesh and then insert, you can have a proper sizing on these geometrical domain. So as I click on that, first thing that software asks is the geometry. So what I'm gonna define the size for is the body or the volume of the air. So I have to select the body. And in order to select the body, you have to pick up these volume or body selection option. So as I click on that, I would be able to click on each of the bodies in order to select them. So for now, I wanna draw and define the size of elements on this body, which is air zone, so I apply it. And next, it's time to define the element size. But as I said before, the other zone is gonna guide us through generation of elements, and I'm not gonna spread the elements with a specific size all over the domain. I'm gonna have denser mesh grid around the vehicle. So this is why I changed the type to body of influence option. And now we will be able to select the body of influences, and actually we've got just a single card, so simply select that and apply it. And now I would be able to actually define the exact element size for this domain. And based on my experience, it would be 0.1 meters for this actually simulation. But it is not ended, and I'm gonna do two more steps. And because this is actually aerodynamic investigation, the flow separation and wake regions are actually included. And one of the key important regions for us is around the walls. I mean around and then in the vicinity of this ground, beneath the car, and actually around the car. So this is where we actually use boundary layers or boundary layer mesh grid. And in order to have that, what you have to do is to once again right-click on mesh, but this time insert inflation. And just like always, the software asks for the zone that you're gonna have the inflation inside it. Of course, this would be, again, this air zone. And the boundary would be selected not by its geometrical selection or the name selection. I haven't named these boundaries, so I'm gonna keep the geometry selection. And instead, for the boundary, I have to select each of the boundaries that I'm gonna generate the inflation on it. So as you can see, automatically the software pick up this face or surface selection option. So you'll be able to select just the surfaces. So as I said, because we're going to generate inflation over the ground, we have to select the ground. And I have to change the view to see the button sign of it. So by pressing the wheel mouse on your mouse, you can have and change the view. So I select this ground side and apply it. And I'm going to keep the inflation option to a smooth transition, so the software will try to have a smooth transition from the bounded layer up to these elements generated in the vicinity of the bound layer. But I'm going to decrease the layers of the bound layer to 2. And once again, I have to insert another inflation, but this time for the car walls. So again, I pick up this body selection option to select the air zone. This time for the boundaries, I have to select the car walls. So it must be very hard to select one by one the sides, and you'll maybe miss one of the sides, and it will lead to error in next generation. So I'm gonna normalize the view to ZY axis, and instead of selecting one by one the sides of the car, I'm gonna change the peak mode to box selection. So now, as I draw a box, by drag and dropping the mouse, all of the sides inside this box would be selected. So all I have to do is to draw a box in this region where the car is actually located. And now you can see that all the faces are selected, and I can apply that. So by now you can see that 175 faces are included for the car. So if you wanted to select all of them one by one, it would actually and surely result in error, and you would miss parts. So for this inflation over the car, I'm gonna keep the layers to 5 layers, and actually the smooth transition method would be activated. So I can say, we're done with the mesh options, and finally you have to click on Generate button and let the software to produce elements. So you can see that it is processing, and you can see the process here. Alright, so it is actually generated, and I have to pause the video because it took a little while. So now let's just get back to our model to see what has just generated. So first thing that you can check is the statistics part. As I expand this here, you will see the total number of elements that are generated. So for this model, based on our options, I can say it resulted in 3 neon elements, and these are all tetrahedrals and actually the wedges around, which stands for bound layer. But let's have a brief look on our model. So from this side, I'm gonna actually create a section view to see what's going inside. So down here in the section planes, you'll see an option that can let you create a new section plane. And then you have to drag and drop a line in order to cut the model. So I do it from up to down, and now you will see the generated model. And besides, in order to have a 3-dimensional full elements view, you can pick and activate the show whole elements option here. And now you'll see the generated tetrahedron elements. And let's what's going inside. So as I zoom a little bit, you'll see the generated elements that are smaller around and behind the vehicle. And as we get through the other walls of the main, the size of them are actually increased. And this is actually what we have done in order to decrease the number of elements. So around the ground zone and actually around the car, you will see a perfect downhill layer that can help us through accuracy and precision of our model. And it is actually something essential in our aerodynamic analysis. So I can say the geometry model and mesh part is done, and there is one more left actually thing in here, and it is creating name selection and names for each of these boundaries, so we can use in our model later on. So I uncheck this box to have the full view and get back to the detail stuff, and we are done with the mesh part. So I close this section and insert click on geometry. So one more thing is that as you saw, the body of influence part has just disappeared, and it wouldn't take into account to our elements, and it wouldn't be taken into account later on in our solution. So let's get to our second step in Ansys meshing. We're gonna select each of these boundaries and name them. So once again, I pick up this face selection option, and do not forget to get back to a single selection option. And I'm gonna select and start from this side, which is our inlet. So I simply select that and right click on our blank space and find create name selection. Then you have to just define a name for that set. So for this boundary, of course, it would be our inlet, so I call this just inlet. And then for these three walls, and do not forget that right now the control button is actually pressed, so I can have multiple selection. And for these three phases, I'm gonna use symmetry name. You'll see what would be the effect in the solver, and we will have a brief explanation about symmetry boundary condition later. And finally, the outlet. And actually the ground. And there is one more thing, and it is the car walls. So once again, I have to change the selection option to box and select all the faces and name them as, for example, car wall. Alright, so I can say and check in my three outline, all the boundaries are specified, and we can quit Ansys meshing. Alright, so we are done with this, and now we need the solver. And our solver in the simulation would be Ansys Fluent. So you can find the Fluent module right here. I have to drop it on the mesh. So the mesh would be automatically actually transferred to the setup or the solver. But I have to keep it updated. And you can find this update button down here. So select update and wait for the software to transfer .msh format, which stands for mesh format, actually finds to be transferred into the solver. Alright, now it is checked, and by just double clicking on setup, you'll see the launcher of Ansys Fluent, in which you can increase the number of processors. For you can increase that based on your computer system. So for my system, I can increase that up to 8 processors. Alright, so the solver has just loaded, and we can start from top of it, the setup section and general tab. So this is where the software asks for general assumptions of its simulation, and on top of it you will see solver tab. We've actually got two different and distinct options. One is pressure based and the other one is the gas based. you have to know that the pressure-based solver is mostly used for incompressible fluids or where we have low speed flows. And with low speed flows, I mean low Mach number, where we have usually less than 0.3 Mach. And in these cases, the density are negligible. So, we can keep it for this simulation because we already know that we're not gonna have a higher Mach number of 0.3. And in aerodynamic analysis of a vehicle, pressure-based solver would be activated. But for density days, of course, it's actually vice versa. In cases where the density is not negligible anymore, and we have to take into account the effect of that, for example, in compressible flow or high-speed flows, we have to cheat against the base solver. Next, it's for the time mode. As you can see, we've got a steady and transient solve mode in Ansys Fluent. The distinction between a steady and transient time modes is actually fundamental. And in a steady state condition, the properties of the system, such as velocity, temperature, pressure, or other variables, do not change with time. And this implies that any time derivatives in the governing equations are zero. So for this simulation, we actually again gonna keep a steady state time mode, and we're gonna investigate the results and behavior of the flow pattern around the vehicle when it reaches its steady state condition. And finally, don't forget to activate gravity in order to consider gravitational acceleration effects on our model. So considering these origin, you will see that we have to draw and define the gravity in negative direction of y-axis. So simply put 9.81 and don't forget the minus mark. Alright, we are done with this general tab, and let's expand the model section in order to define a viscous turbulence model. Alright, so as can be seen in this window, we've got plenty of options provided by Ansys Fluent. But in this simulation, we're gonna use K omega as the model. Actually, turbulence models in Ansys Fluent range from simple one equation like Spallat-Hornhaus model up to two equation models like K epsilon J omega, and each of them has its own benefits. But when it comes to J omega system model, it is highly recommended for aerospace or aerodynamics analysis applications because it offers an excellent balance between accuracy and computational costs, especially for band layer flows, and it handles both near wall and free stream visions. And this is actually what can suit our simulation because we've got downward layer separation over the cog and actually the wake regions that are expected to form behind the vehicle. So I keep K omega as the model and just click on OK to apply it. And now I close model section to open materials step. So in here you'll see that by default the software has air as its one and only fluid, and aluminum has its solid. So we already know that for this fluid region, which is our air region, the air is actually applied, and you can check that from cell zone condition because we've got just one pair zone. You can check the settings in here to see the material that is applied on this. From here, you will see the list of available materials, but as I mentioned, because we don't have any other option provided in Ansys for now, the air is automatically applied. And now it's time for the most prominent part of the simulation, I mean boundary conditions. So in here, you will see a list of different conditions, and on top of it, you will see the inlet boundary. So as you can see, the type of this boundary is on velocity inlet. You'll have a list of different conditions, but regarding the fact that they're going to define the magnitude of the incoming airflow, I'm gonna keep velocity inlet boundary. Then In the settings window, you will see different thermometers that suffer as. But for this simulation, I'm gonna just define the velocity magnitude of air for incoming flow, which is 85 meters per second. And beneath that, there is a box titled turbulence that has some related specifications to turbulence effects. So for this simulation, I'm gonna decrease the turbulence intensity to 1%, and instead for turbulent viscosity ratio, I keep 10. So you may ask and wonder, what are these parameters? Actually, turbulence intensity and turbulent viscosity ratio are important parameters used to define the turbulence characteristics at the inlet boundary. So these parameters have to accurately represent the flow conditions into the computational domain. And the typical values of turbulence intensity, for example, where we've got low turbulence is beneath and below 1%, and for high turbulence is mainly higher than 5%. And in this relation, which is actually 1%, it is actually the mostly common value for external flows with low turbulence. And next, for the turbulence viscosity ratio, the actual common value for external flows is 1 to 10. So for internal flows, it can be higher, sometimes even more than 100 or 1,000. So I keep these settings and apply them. Next, it's time for outlet boundary, and as can be seen in here, the pressure outlet type is used. So let's check together the specification of this boundary. The most important parameter in actually pressure outlet type boundary conditions is the gauge pressure, because we already know that this outlet side is in direct contact with the atmospheric pressure. So what we're gonna define in here is the gauge pressure. And as you already know that, if I put gauge pressure equals to 0, it means that pressure on this outlet boundary side is equal to atmospheric pressure, and this is actually what we needed. So I'm not going to change anything in here, so simply close this window as well. And let's get to symmetry boundary that are colored by yellow in here. As you already know that, and these symmetry walls don't have any specifications, and regarding the fact that in these walls there wouldn't be any shear stress, or in other words, the normal variables would be 0, it would act like a mirror. So there wouldn't be any normal velocity applied on them, and we already know that this is air around our computational zone. So this is why I prefer to call them symmetry before in Ansys machine. So this Ansys solver automatically use symmetry boundary type for it. And now it's our last boundaries that are our walls, and then partially got the same condition. So let's start from the car walls to see the settings. And for now, you can see that there wouldn't be any wall motion, because the motion of wall is actually specified by the incoming flow. So we need to consider the wall of the cars as a stationary wall. But this is very important to know that the shear condition is a no-slip condition, and we have to satisfy the no-slip shear condition on the walls, because each deal resulting actually forming of the boundary layer and separation. So this is very important, and it's a fundamental assumption in fluid mechanics. And the other fall, which is the ground, has the same boundary conditions. So let's just check it, and you'll see that the stationary wall and no-slip shear condition is maintained. Now it's time to have the methods which actually beneath the solution section. So in here, two important sections of the solution are located. One is the pressure velocity coupling scheme, and the other one is discretization method that are provided in Ansys Fluent. So as you can see in here, Ansys Fluent offers 4 different coupling schemes for pressure velocity couplings. And don't forget that these are available only if the pressure day solver is used. So for this simulation, I'm gonna use simple algorithm because this actually scheme is widely used in CFD solving for the Navier-Stokes equation in steady state simulation. And for additional information, you can know that it's one of the segregated algorithms, unlike coupled algorithm. So it will solve the momentum and continuity equations to handle pressure velocity coupling. And it works by guessing and then correcting pressure and velocity fields successively and make it efficient for many flow patterns and problems. So for this simulation, I'm gonna select it and use it, and instead beneath that for a spatial discretization box, the second order schemes were implemented across all the variables, including the pressure gradient and actually the momentum and turbulence. Of course, all of them will result in high accuracy for velocity fields, for pressure gradient, and also turbulent transport equations. So let's scroll down to find the residuals beneath the monitors. So these are just residuals. You may have heard about them. And in CFD simulations, these are numerical measures for imbalance or error in the conservation equations, such as mass or momentum. And for each cell in the computational domain, this will actually calculate the error considering the absolute criteria that we are defining in here. So as soon as I start the solution, you will see the ratios that are reported beneath this region in the console part. So these are actually typically monitored during the iteration process, so we can check the convergence. But you have to keep in mind that these convergence, the convergence of ratios, wouldn't guarantee convergence of the solution. But these are just called primary convergence criteria. So I wouldn't change these absolute criteria. I'm gonna keep them and close these ratios as well. So how can we guarantee a convergence, and how can we sub the solution so we actually make sure that if we have reached the convergence? For this purpose, main option is to monitor a specific and sensitive and even important parameter during the calculation and monitor that during the solution. So as soon as it reaches a constant value, we can be assured of our convergence. So you may ask where to put it. In order to define this parameter, you have to right-click on Report Definition box and then define a new report. For example, in this simulation, of course, for example, drag force applied on the car could be a great choice. So I'm gonna make a surface report by area weighted average type, in which we can define a name in this box, and then you have to select the field variable that you're going to calculate it in. So, for example, as I said, on this, for example, simulation, maybe the velocity at the outlet could be a perfect option. But as I mentioned, for this simulation, I'm gonna monitor the drag force applied on the car. So you can find that not in this list of variables. To monitor the forces, once again, you have to get back to here and define a new force report. You will find the drag, lift, and moment force down here. So I select drag force and call these reports, for example, the drag F, which stands for drag force. And for default report output type, you can have the drag coefficient or drag force. I'm gonna use encrypt the drag coefficient. And in the zones part, you will see all the walls that you can report and calculate the drag force on them. So as I mentioned, the drag force on car walls is important to us. But the most important part in here is the direction of the force vector. So as you already know that the drag force would be in the direction of the airflow at regarding this origin, you already know that it would be in negative direction of the axis. So I have to change the force vector to -1 in the direction of z axis, and this will show us the exact drag coefficient. After doing all of this, click on OK button, so you will have drag coefficient or your specific report beneath here. And as soon as you start the calculation, your parameter, the desired parameter will be shown in each iteration. Alright, so I can say it can be actually near the end of the solution part. So in order to start the simulation, we need an initial guess. And in this simulation, once again, I'm going to use a sun initialization option. And you may wonder why, because this is actually the simplest method provided in Ansys Fluent, and it sets uniform values for all flow variables across all the entire computation domain. And this can help us for convergence. Of course, it wouldn't be as fast as heartbeat initialization, but it is not something sensitive to us in this simulation. So after checking initialize button, the initial guess values would be put into momentum equation, and we can start the calculation from one calculation option box. The software asks for number of iterations. Of course, for now, for example, I put 3000 and click on calculate button, so the software will start the solution. And I can check the drag force, or better to say, the drag coefficient in each iteration. So let me show you in here. So as soon as it reaches a constant value, I can stop the calculation by pressing the stop button up here and check the results. So for now, let's just have maybe some iterations. Of course, these are 3 million elements, and this can be a little bit hard for my system to process. So you can see that the residuals are shown in here, and the drag force is shown in here. For each iteration, it is updated. Very well. So the solution is already done, and as soon as we've reached a constant value with this drag coefficient, I manually stop this solution. And you can see nearly 2,300 iterations were performed. But the fluctuations reaches a kind of tight range, so I stopped it, and we already know that we have reached actually convergence. And these are residuals that has reached convergence very soon after 1,000 iterations. This is why I promised you that residuals cannot guarantee the convergence, and you have to monitor a specific and sensitive parameter with you. So I'm gonna close Ansys Fluent and instead do some more steps in order to get to the results. But of course, because we're going to have a comparison, I did these steps and established a new change for the Sedan model. The Sedan model of the car, 206. And you actually need to follow exactly the same steps. And finally, I'm going to use a new powerful tool provided by Ansys in order to actually visualize the results with better quality and more details. And this software is called CFD Post, which you can find in here. If you scroll down, you will find results up here. So simply I drag and drop it in the blank space, but I have to connect this solution to these results. But due to the comparison aim of this study, I'm gonna connect the Sedan model as well. This is actually one of the benefits of post-processing in CFD Post. So by those decon results, I can let the software to be loaded. Alright, so this is it. You can see the CFD Post workspace. Let me explain to you some of the parts of this software. First of all, beneath this admin section, you will see both cases. I mean the Fluent HB, which stands for hatchback, and also the SD, which actually mentions the Sedan model. But for each of them, you've got access to all of these actually boundaries, and you can apply and show each of the boundaries by just checking these box near it. So one of the most important parameters and options that we've got here for comparison cases is the view type. So if you click on this tool, you can have and change both views. And in order to have an individual and single view, I'm gonna divide it into two. So now I can have view 1 for one of the cases and view 2 for the other case. And in this way, I can have the simple comparison by having both of them in a single frame. All right, so let me, in the first step, let me show and indicate the car itself, which was called wall car. So I put and check this box near it, and by just double-clicking on that, you've got access to some of the related options to its visualization. And on top of it, I'm going to change the color to something like gray, so it would be more like car. All right, and you can see that simply these changes are applied to both cases, and we can have a single change, but view and apply it on both cases. All right, so let's start from creating plane at the middle of this geometry, which will be called a section plane, in which we can display the contours or the velocity vectors on that. In order to create that, you will follow the location toolbar and then plane. So I'm going to call this plane mod, the simple and default name. And now I got access to the domain extents. And for this plane, of course, regarding this origin, it would be in ZY direction. So I'm going to change the method to ZY in the first place, or YZ. And I think regarding the origin and the reference origin and the initial accepting as is a space claim, the X value of 0 would be put just in the middle. So let's apply it and see what is happening. So this is the plane that we've just created, and you will see that it's actually cut the car from the middle, and now we can create contours on that. So let me hide this plane and instead use contour tool up here and create a contour one in order to display some of the related variables that can help us through the analysis. So the first thing that you have to change is the location. Of course, I'm not going to put this contour on the ground. Of course, it is going to be on plane 1 that has just created. So beneath that, you will see a box in which you've got access to some of the variables, including pressure, density, velocity in each of the directions, and if you scroll down, you will have access to some other parameters. So let's start from pressure, as it may help us. And for range, of course, I'm going to change that to local, because on this specific plane, these local values would gives us more accurate and better visualization rather than using the global reference. So as I click on apply button, I can wait for the software to draw and display the pressure distribution along this section plane. And here it is, you can see that. And what is actually eye-catching in the first sight is the pressure and its accurate increment in the front of the car. And it's completely natural. But as I'm going to have a comparison, this may not really help us, because I can see any difference between these two pressure distributions for now. And note that you can increase the number of contours to have there are more contour bands, and this will increase the accuracy. And now you will see that you can have the values by using 15 different contour bands. So let's skip from these, let's just say pressure distribution. Maybe it cannot help us to this analysis, and instead I can have the velocity. So I change the variable to velocity stream and apply it. Alright, so as you can see, the velocity is actually created. And one more thing is that because I'm going to change the views to have comparison, it's better to lock these views. So up here you will find an option in which you can synchronize camera in this place. So yeah, as soon as you change the view in each of these contours and views, the other one will be changed automatically. So let's discuss this contour distribution of velocity. And one more thing is that by just drag and dropping by the right click of your mouse and drawing a box, you can zoom in. Alright. So what is very actually noticeable in the first place is the significant differences in airflow behavior between these two models. The hatchback, as you can see up here, exhibits a more abrupt flow separation and at the rear, and resulting in a larger wake region, and of course in sedans, because of its extended trunk profile, it allows for a more gradual flow separation. It will it is evidenced by more organized streamlines and the smaller wake regions. So these can really help us to getting to know about the wake regions behind each of the models, and what is more actually visible here is that both views are actually using and showing the hatchback. So I'm going to change the view to, instead of all cases, to the Sedan model. So now you will see the Sedan model's pressure distribution, and now it would be more visible. And one more thing is that I'm gonna actually show the Sedan model as well. So I extend the boundaries and instead use wall car, and again color it by gray. And now you can see the changes. Alright, so the wake region is completely actually in contradictory with each other. I mean the hatchback model or the other one. And let me again change it to Fluent hatchback model, and now it is correct. So you will see the flow separation. It is completely abrupt flow separation on the hatchback model, and this actually results in drag increment, and we will get to that. But for the Sedan model, just because of this extended trunk on the rear, it can help to prevent flow separation and actually at least delay it. So let's just get to the other one. For now, I'm going to hide the contour one and instead use a streamlines option up here. So now let's discuss the actually 2D surface streamlines that can help us to see the wakes behind them. So on the surfaces bobs, I'm going to change it to plane 1. Again, I'm going to display the streamlines on the sectional plane, and before doing anything else, I just apply them. Just let's see just what the default values would give us. Here is it. You can see that the wakes are not very illustrated, so I'm gonna change and increase the number of points, so it may lead to better visualization. And still, you can see that by increasing the numbers, I cannot have better visualization. So this may be from the start from option. You've got plenty of options, but mostly I use the face centers, in which it use the centers of each of the cells in order to create the path lines. or let's better say streamlines. And now you can see that it gets better, and now I can see the vegs behind it. And by increasing the number of that, we can have more streamlines, but notice it will actually increase our computational costs. But here it is. You can see the streamlines right now, what we've said about the veg regions, the separation point, and actually the vertices formed behind the cars are depicted. And you can see a big vertex on the rear of the hatchback model, while with the Sedan model, we've got vertices just behind the car after the trunk with two small veg regions. And one more important thing in here that may help you through your analysis could be three-dimensional streamlines. But this one would actually result in higher computational cost. So I change the type to 3D streamlines, and this time I'm going to start from the inlet boundaries. So let's have these 3D streamlines as they start from inlet boundary. But again, you need to increase and change the parameters in order to have better samplings. For example, once again, I use the face centers, and you will see the actually streamlines in three-dimensional and how they flow over the car, not only in hatchback model, but also in Sedan model. But this may not be very clear to you. It may just be appropriate for visualization in your report, and for better analysis, you need to know more details about that. This is why we actually try to have the results in 2D. So let's hide the streamlines and get to another perfect option that can help us through analysis, and this would be the shear stress applied on these cars. So once again, I create a new contour, but this time I'm going to change the location to the wall car because shear stress is actually applied to the cars. So do not hesitate to change it to wall car. And in the variables list, I need to find the wall shear stress. So you will see that up here. And again, I'm changing the range to the local to have better visualization. And for now, let's just keep this 11 default value to see what we've got. All right, so let me zoom a little bit. And now you'll see the wall shear stress distribution along the car. Of course, by increasing the number of contours, again, we can have a more smooth pattern. And but here we can have the stress applied on these cars. So for now, you can see that the most difference is around the car when it gets to its rear. Of course, because of this actually trunk that is added to the Sedan model. So the analysis of the shear stress contours highlights distinct stress distribution across vehicle surfaces. And as you can see up here, the hatchback model shows high shear stress concentration along the roof to rear transition. So this is where I'm talking about. And you can see this fast transition in the stress concentration. And this could lead to increased local drag and, of course, potential flow separation points. But in the Sedan model, exhibits more gradual transition with lower peak shear stress in this region. It's suggesting better overall flow attachment. So the Sedan does not show increased shear stress at the trunk's trailing edge, indicating a potential area for flow separation. And this is how we can analyze these shear stress distribution. And finally, I'm going to show you one and another spectacular option of post-processing in CFD Post software, and it is the velocity vectors, which you can find just near the contours option. So again, I'm gonna keep the default name and instead change the location to plane 1 and apply them to see the distribution and velocity vectors. Actually, I believe that this can be a best option in order to analyze the forces, and by depicting these velocity vectors, you can completely see and analyze the vortices behavior on the rear of the cars in each model. And this may help in your article or report, and you can export them to your computer. Alright, so I think one more thing is left here, and it is the turbulence effect behind the cars. And in order to have them, once again, I get back to the cars, contour, and instead I change the variable to turbulence kinetic energy. Actually, these are very important, and these are actually the main cause of the separation and the wedge. So I'm going to display them, and these are actually, once again, change it to kinetic energy. And here is it. Let's have a normalized view. Then these contours are actually showing the best differences of hatchback model and the Sedan model. The turbulence kinetic energy plots, as you can see, provide crucial insights into the weight characteristics of both models. The hatchback generates a more compact but intense turbulent effect immediately behind the vehicle, but you can also check the values of the turbulent kinetic energy, it reaching up to approximately 40, but in the other hand, the Sedan produces a more elongated wedge structure with a slightly lower peak turbulence kinetic energy values. And these contours are actually suggesting that the Sedan's extended profile allows for a more gradual pressure recovery, potentially reducing form drag. And we're actually talking about drag, so have in order to have some values that we can have a comparison between these forces, you can use the calculator up here. So as you get through the functional calculator, you've got different functions, but of course I'm going to have the average forces. So I change the type to the average and change the location once again to the car vol, because the forces are acting on the car vols. And of course, I'm going to report it for both cases. So keep the all cases option. And finally, change the variable to wall shear stress. Of course, regarding the fact that the drag force would be in Z direction, we can have the wall shear in Z direction. And this actually gives us the drag values. So by just clicking on calculate button, we can have the shear stress along Z-axis for each of the cases. And in here again, it is completely visible that the values for Sedan model is increased. And this may not be very clear when it comes to drag force, but just regarding the wall shear stress, it can help us. And one more thing is that we showed you how to define a report in Ansys Fluent to report drag forces, and based on our best options and based on our results, the results for hatchback model would be lower than the Sedan model, and this represents a significant reduction of approximately, as I calculated, it was about 34% in the forces of the Sedan model. So it will lead to better stability in the Sedan car, and we actually know that this has resulted in, and we can have the manufactured cars, and this is actual proof. So the analysis shows us the same results, and this can lead us to optimization within the design of the cars, and we can have and benefit from the simulations for the next models of the cars.